Hi everyone. This is a completely optional video, which means here we are going to see one example of C code that we are going to translate into assembly. So the purpose of this video is to make you understand that how compilers are making use of the addresses, right? Do you remember I told you that if I'm writing, let's suppose move R1, 1000 or something like that, then how compiler is actually generating these addresses. So this is one thing that is still unanswered. So in this particular video, I want to answer this, and this video is completely optional in the sense that you don't have to watch it now. You will get to understand these things later in computer organization. So currently make it completely optional. If you want, you just watch it. If you don't want, don't watch it. Okay. So let's just see that how a C program can be converted into some assembly code. So this is a C program, very simple C program, and here I just want to make you understand that how we are converting that to some assembly code. So let's just see this. See, there is a main function. That main function is calling this func function, right? So this is func function. So this main function is calling func function, and this func function is having some statements. Now let's just see that how we are or how compiler is converting that to assembly. So if you notice that this is a main, this is a code of the assembly of main function. This is code for the func function. Now there are some registers RBP, RSP, these are being used. So let me first explain you that what does this RBP, RSP or these things, okay? Let me quickly explain you that how does it work. So see, whenever you run any program, there is something called, whenever you call some function, there is something called activation record, right? Activation record. So this activation record get pushed whenever you call a function in the stack. So this is one stack, and if you're calling main, then main activation record will get pushed. If main is calling some other function, let's suppose func, then func activation record will get pushed, right? So this is main activation record, this is func activation record. Okay, so I hope you understood. So that's how we are pushing the activation records. Now the interestingly, this stack that we are talking about here, so this stack is basically can grow upwards, which means it depends on the architecture whether you are going upward, or it can also grow downward. So what do I mean by that? Let me just show you. See, suppose you have something like this. Your stack may be something like this also. Okay, so your stack may be something like this, which means in this case stack is growing downward. So let me just rewrite it. This is func activation record, right? Okay. So what we are doing, we are basically saying that either stack can grow like this or stack can grow like this, and very easily you can also check by printing some address. If you print some address in the main function and then you print some address in this func function, then you will get to know that stack is growing upward or downward. It will depend on the implementation. So stack either can grow upward or it can grow downward. Let's not worry about it. Okay. So basically we push the activation record of the function in the stack. That's what I want to say. Whenever you call any function. Now, there are two pointers that get maintained using two registers. One is called base pointer. Okay, this is called base pointer. Another one is called stack pointer. This is stack pointer. Now, there is a register. Generally name can differ. So there is a register, let's suppose register a base pointer, register a stack pointer. So which holds the value of base pointer, which holds the value of stack pointer. So what has happened? Let's suppose that whenever you have some stack, then generally, so I'm talking in general. Okay, generally it happens that the stack pointer tops the top of the stack, and the base pointer will depend on the function. So it will point to the bottom of the function, start of the function. So currently, let's suppose you are pushing this function, then RBP is pointing the start of the function, RSP is pointing to the top of the function, or maybe you can say the top of the stack. So basically, it is a stack pointer which points to the top of the stack. There is something called base pointer which points to the it points to the start of the function. Okay, it's not like that you have two base pointer for every function. I mean, for these two functions you have two base pointer. No, the base pointer initially was this, and it will get modified to something else whenever you are calling this function. So we will come to this detail later, but for now, if you don't know what is stack, if you don't know what is, I mean, what is this activation record and all, actually these are the things which you will get to see in the other subjects. So stack we are going to see in data structures, activation record we are going to see in the compiler design. So these two are different components that we are going to see later at the later point in time. So that's why I'm saying this particular video is completely optional video. Okay, so now let's just understand this particular piece of code, that what they are saying. See what we have a main function. This is the main function, and then we are calling we are basically having this particular assembly of this main function. Now let's just see step by step what is happening here. Maybe what can I do? I can just make some space here to explain you the things, right? Okay, so first we are having these instructions in main function. So let's just see what we are doing. We are having one stack, and let's suppose this stack is growing downwards, which means that you are having some lower address 000 here, and some 010c, some upper address, which is the first address of this stack. Okay, whatever it is, so let's not worry about it. So now what I'm saying is that you are having one stack which is growing downwards. Now whenever you have a stack, that's very default that you also have the stack pointer. So the stack pointer in this particular example, we are storing in a variable. That variable name is RSP. So this is our stack, and the stack pointer is in RSP. Now what we are doing is basically something like that. We are pushing the value of RVP. So see, whenever we call any function, whether it is main function or any function, so there is something called entry, there is something called exit. So some entry and exit are actually predetermined. I mean, are the fixed set of instructions. So if you notice, this is something called entry, which is fixed in main and in function also, and something called exit, which is fixed in main or in this function also, right? So this is exit, this is entry, which are fixed, right? This is entry, this is exit. So anyway, we will just see that what are these, but generally these are the fixed set of instructions that we have, right? Okay, so maybe I can just keep it here this same, and then maybe I can just go to the next page. Okay, so let me go to the next page. Yeah, just give me a second. Okay, so let's consider that this is our image. Okay, so cool. So what I'm saying here is that you have one function which is main function, and then first you are pushing this RPP, right? See, these are the entry exit which are fixed, but let's just understand this step by step. You are pushing the value of RPP. So what is RPP? As I told you, there is a base pointer or the frame pointer for every function. So initially, whatever is this value, let's not worry about it. So you are pushing it, pushing the value of RBP in the stack, right? So this is RBP. That's what you are pushing. Now what you are doing, you are saying that okay, you are moving the value. Okay, whenever you push, first of all, whenever you push, at that time, I mean, it depends on obviously the architecture, but in this architecture, whenever we are pushing, at that time we are also incrementing the value of RSP. So now after the push has happened, so I will say after the push has happened, now the RSP will start pointing here. Okay, and the push is now complete. So till now only I can say the push is complete and RSP will start pointing here. So you will say that after this push has been completed, so you will be having this particular architecture, right? So see here the push is complete. Now maybe I can just blur this. RSP is not pointing here anymore. Okay, now this push has been completed, and this RSP has been incremented to the next value. Okay, you have pushed the value of RBP, whatever is this. Okay, RBP is one register, whatever it is containing, you will push it here. Now you are moving this RSP to RBP, which means that you are having one register RBP which will be containing same value as RSP, which means this after this instruction the RBP will start pointing here. So now this is also done, right? So basically, like if I just tell you step by step, currently whenever you do this, RSP will start pointing here, and then whenever you do this also, then RSP and RBP both will start pointing here, right? Okay. Now this RSP minus 16, so it is you are subtracting RSP with the 16. See, again these instruction and these kind of things will anyway come in the computer architecture later. So currently we are just understanding this as an optional video, which means even if you don't understand anything, this is completely fine. See, currently you might not be even knowing what is stack, but that's okay. Okay, like in the computer architecture you will see what are these instructions. In the data structures you will see what is the stack and all. Okay, so this is one optional video that we are currently seeing. Now you are subtracting 16 from RSP. So since this is the higher address, and if you are subtracting, then it means that you will go below, right? You are subtracting 16, so maybe you are going some 16 bytes down. I mean 16 address down. So maybe let's suppose this is 4 bytes, 4, 8, 12, and then 16. So if you subtract 4, you will come here, 8, 12, and then if you subtract 16, you will come here. So basically after subtraction, you will say that RSP will start pointing to this particular location, because this particular instruction, which is the subtraction, will basically make this RSP point to this particular location. So RSP will start pointing here. I hope that is fine, right? So these are, let's suppose 4 bytes. Okay, this is again suppose 4 bytes. So these are the 4 bytes. Anyway, let's not worry about it. But yeah, so I have like just for the sake of simplicity, I'm just saying it. So everything I have just kept it as a 4 bytes. I mean just to manage the diagram. Okay, cool. So these are the 4 bytes of memories. Okay, so now currently RSP is pointing here. Cool. Now what we are saying, now let's just go to the next instruction. So this instruction is also done, and now let's just go to the next instruction. Now what we are saying, that this move d word ptr. So basically there is some addressing mode involved in this, so let's not worry about it. Basically it means that you go to this RBP minus 4, wherever is this RBP pointing. So currently I think RBP is pointing here. You go minus 4, which means here, right? So which means at this particular location, and then you put 0 at this particular location. So basically, yeah, so you will be putting 0 here. I mean, see, RBP is here. If you put this 0 at RBP, then you will putting here, but you are putting at minus 4. So basically you are putting 0 here. That's perfectly fine. I mean, you can put here or here. It will depend on the implementation. So let's not worry about it, but I'm just executing the instructions. So RBP minus 4 will, you are putting the 0 at RBP minus 4. Cool. So now this instruction is also done, right? Now let's just go to this instruction, which is saying EDI, 5. So basically there is some register EDI that they have taken. Generally this register is by convention is used to store the function argument. So if we are passing 5 here, then this EDI is one register that is actually storing 5. So okay, so EDI is one register which is storing 5. Now you are moving 5 in this EDI, which is here, this 5 is one constant. Cool. Now this instruction is also done. So we have completed these instructions, right? Now let's just call this function. Now whenever you're calling the function, you will go to this particular location. I mean this is one you can say one subroutine or something. Okay, you will call the function, and then here what you are doing, you're pushing RBP. So what is the current value of RBP? See, this RBP is currently pointing here, right? Now you will be pushing this. Push means this always work with respect to RSP, which means stack pointer. So wherever this stack pointer is pointing, you push RBP value here, right? Whatever is the RBP value. So you will be putting RBP value. Whatever is this address, you will be putting RBP value here, right? Now you are saying, since you are pushing, okay, so since you are pushing, that means that now RSP will start pointing to the next location, because the push make it happen. Okay, so basically you will say that this instruction is also done, and after this instruction, this RSP will start pointing here, and RBP you have already pushed. Okay, so maybe it is fine, or if you want I can just go over from the starting. See, I mean, initially you are pushing RBP. So your RBP will be here. Whatever the initial value of this, let's not worry about it. And then you are pushing means you are incrementing RSP also, right? So this instruction is done. And then you are saying move. Then whenever you are saying move, so there is one RBP register. You will be moving RSP value to RBP. So both are pointing to the same location, right? And then once you execute this -16, so it will come down. Then you execute this -4, 0. So wherever it is pointing, come -4, I mean, come 4 down and put the 0. And then you are having one register. So after executing this, you are having one register EDI. You are having 5 here. So you put 5 in that register. Then you call this function. And once this instruction is done, then it means that you are basically pushing RBP, and then push means you are incrementing this particular value also, right? Okay. Now what you are doing now, if this is fine, then you are basically executing this. This instruction means you are basically moving RSP to RBP. So whatever is the RBP initially, now RBP won't be pointing here anymore. Okay. So RBP will be pointing to this particular location wherever RSP is pointing. So RBP will start pointing here, right? Now you are executing this line, which is d word ptr RBP -4, cool, comma EDI. So what does this mean? It means go to this location RBP -4. Okay, go to this location. See, there is some addressing mode involved in this. Let's not worry about it. But it means, it essentially means that go to this location RBP -4. So RBP is currently pointing here. Okay, go to -4, which means you go to this location. -4 means you go to this location, and then at this location put EDI. EDI is 5, so you will putting 5 here. So you don't need to worry about that why we are leaving out some location here. Maybe because of some reason, like compiler has decided to leave out some space. Okay, not a much space it is. It is just a 4 byte of space, but anyway. So these are the 4 bytes. These are the 4 bytes. Now I think which instruction we were executing. Yeah. So this instruction is also done, right? After this instruction, you will be having something like this. See, also this EDI, if you remember, EDI was holding this 5. This 5 is actually something we have passed here. Okay, so I think in this program, I'm having 5 everywhere, but okay, it should have been better if I could have taken 3, 4, 5. Okay. So, okay, let's just do one thing. Let's just work with this example, and then we will move 3, 4, 5 later, and then we will see that what we can, how we can, how we can modify this particular code. So I think only the difference will be here. This will be 3, right? It will be 3 if I'm writing 3. Anyway, but you know that this 5 is in EDI, and if I'm writing the EDI, it is basically this 5 will get copied to argument. So basically, I'm referring here the argument variable, right? This is the argument variable. Okay. Now let's just execute the next line, which is RBP -8, and now you are putting this constant 5. Okay, this 5. So maybe it is because of this, right? Because line by line, if you see, then it is because of this. So RBP -8, RBP is here, -4 is at this point, -8 is this point. Now you are again putting 5, which is because of this int a equal to 5. So if you're putting 5, you can say that this is a variable name a. Actually, for the compiler and all, like for the assembly, the variables doesn't exist. Only the memory locations exist. Okay. So that's why you don't see any variable a and this argument and etc here. The G is a global variable which is also representing one memory. Okay. This is called absolute addressing mode. But let's not worry about the addressing mode and all currently. But I hope you understood that what do I mean by saying that I have executed this line. It means that you go to RBP -8 and you put 5 here, right? Okay. Now let's just execute this line, which is saying that d word ptr g5. So G is a one global variable. So it is having one separate memory that is not in the stack. So global variable are always in the separate memory that is called static memory, right? So you will be putting 5 here in the static memory. Okay. So I hope you understood this. So there is some different memory. Don't worry about this memory, but that memory is not in stack. That's what I'm saying. Now pop RBP. See, push and pop always with respect to stack pointer. So generally, like, we don't increment the stack pointer, which means every time there is no need to increment the stack pointer whenever we are pushing something. But if I'm executing any instruction, push or pop, it is always with respect to the stack pointer. So if I'm saying pop RVP, it means that you are popping wherever is the stack pointer. See, stack pointer is currently here, right? See, this instruction is done. Now I'm trying to explain you what happens whenever you are doing pop RVP. So it will pop whatever this stack pointer is pointing to. It will pop that value, okay, wherever it is pointing to. See, the top of the stack, if you look at this stack, then top of the stack is basically, like, based on the RSP, it is basically this. Like, you don't care about these things. Like, you don't care about these things. You are saying that wherever this RSP is pointing to, pop that value and put that value in the RBP. So pop RBP means put that value in this register RBP. So whatever this value, okay, I mean, actually it is restoring the value. So which means that, like, let me just tell you that what is happening step by step. See, initially whatever is the value of RBP, that is okay. But let's suppose this particular address at the starting address. Let's suppose this is 100. Okay, this is 100. Okay, just for your sake of reference, then this will be 100 minus 4, 96. Okay, this is 100, this is 96, right? And then you are saying this RBP is basically pointing here. So RBP is currently 96, right? And now RSP will be, this is minus 4, 4, 8, 12, 16 and 20, right? So basically RSP will be 80. So currently RSP, this is actually 80. So RSP will be 80. RBP is actually 96. Okay. Okay. At this particular frame, I'm saying RSP is actually 80. RBP is 96. Okay. And this is 100. Now what you're doing, you are putting 0 and these things, that is okay. So maybe I can just copy this. Actually, I just want to show you that this is the old RSP. Anyway, so basically now what you are doing, you are pushing here, you are pushing the RBP. And what is the value of RBP? RBP is currently, if I just tell you the RBP, it is basically, okay, I can put this here. The RBP is 96. Okay, if you look at this RBP, it is 96. So basically you are putting 96 here, right? You are putting 96 here. Now you are putting 96. So this RBP value is currently 96. So here you are putting the 96. Now whenever I'm saying that that you need to pop it, I mean, whenever you are executing this is actually 96, right? This value is 96. That's what I want to tell you. Now it means that you pop wherever the stack pointer is pointing to, you pop that value and put this 96 in the RBP. Which means that RBP, after this instruction, once you say that this instruction is executed, then this is very important to see, then RBP will be getting the value whichever is the top of the stack. So what is there in the top of the stack? See, pop RBP means you pop the value and put that in the RBP, and pop this 96, put in the RBP. RBP won't be pointing here anymore. After this, RBP will be 96. So which means RBP will start pointing to this 96, wherever this 96, I mean, will start pointing to this location. Okay, this is 96. So basically what I'm saying, that you have basically restored everything. I mean, you have restored your RBP. Earlier RBP was this. So this is actually the main stack pointer. And then between the main and between the function activation record, you push this RBP. But whenever you're returning, see, these are the return statement. Whenever you're returning, you basically do one thing. You store that. Okay. I mean restore that, right, using this pop. So now after this, RSP is still pointing here. Sorry, this pop operation will also decrement the RSP. So after this statement, RBP will start pointing here and RSP will also get decremented, just like push increment the RSP, pop decrement the RSP. Sorry, decrement here is with respect to whether stack is going downward, upward. But yeah, basically the RSP will be here, right? Increment, I think it will be increment. Okay, cool. So I hope you understood. So after this statement, RSP is pointing here, RBP is pointing here. Now let's just go to return. So it will return now, right? Now let's just come back here. Now this call is done. This call is done. And now you are executing this XOR EX. So AX is one register that I think holds, by convention, that I think holds a return value. If you're not returning anything, then maybe this architecture is taking 0, because they see, if you do the XOR, which means if you do any value XOR, which means let's suppose 101, if you do the XOR of this same, this will be 000, right? So basically it is one way of saying that you are storing in the AX register. Okay, there is some AX register, let me write this AX, you are storing 0 here. Okay, it is generally reflecting the return value. Anyway, like you can ignore this line. Like you may say that why XOR, why not we are writing move or something like that, right? Why we are not writing move EAX 0 or something like this, move 0 to this. You can write this instruction also, that is also fine. Maybe this XOR is taking little less bytes. Generally XOR takes, I think, 1 byte, and move takes generally 2 or 3 bytes of the instruction. So maybe just because of that they are doing this XOR. This is one hack that some architecture does. Okay, anyway, so you can ignore this XOR. This is generally storing the return value, and if there is no return, then by default it takes a 0 as return value, maybe. Okay, so now you are doing what? Now you are adding RSP to 16. So which means this is RSP. You are adding means you are going upward. So 16 means plus 4 plus 8 plus 12 and plus 16. So once you add 16, you will be here, right? You will be here. So maybe I can, yeah. So basically this instruction is done. Now if you add, then okay. So if you add 16 here, then see, earlier it was pointing here. So plus 4 plus 8, I mean 16 means 4 cells up, right? 1 2 3 4, yeah, it will be pointing here. So now you will start pointing to this particular location, right? So this is the main activation record, and now you are saying pop RBP. So wherever it is, now you will be popping the RBP, I mean popping the value, and you will storing in the RBP. So that's the earlier operation that we did, right? So that is how you can understand this whole procedure. Basically the idea to explain all of this is to make sure that you understand that how the address translation and these things are happening. Like you don't need to worry about the particular architecture, particular instruction, what it is doing, or like or any of this particular syntax. You don't need to worry about it. So basically the core takeaway here is that you just need to know the stack pointer, like what is the start address, right? And based on that, things get start pushing, and whenever you are calling some function, it will push its argument like that, right? So you never need to know, like I mean the physical addresses. You can just assume that wherever you are loading, right, wherever you are loading, from that reference you work with all of this. So this is the stack pointer that is being set by the loader. Okay, and wherever you are loading, based on that you do all of this stuff. I hope you understood. So basically let me just quickly explain this again, maybe it will be better. So yeah, so basically this is the same exactly the same example. So instead of 555, I can do one thing. I can just take maybe different value, maybe 345, and quickly explain you what is happening. Okay, just for the sake of I can say revision. See what is happening. Maybe before that I can quickly go through the step-by-step process that we did. So see here, this tick mark means we have executed this, which means we have pushed the value of RPP, whatever the initial value. I actually don't know, but we have pushed it, and then we are saying that okay, you move the RSP to RBP, so both are pointing to the same location. You subtract 16, now RSP is pointing here. Now you do this, then it means that after the 4 location, 0 got pushed, or you are writing the 0, and then EDI 5 means you are having this register, this is having 5, and then you are calling the function. Then this push RBP means that you are pushing the value of RBP. So RBP is initially here, I think 96, so 96 will get pushed, and then all of this is happening step by step. So you can go through the slides. I made the slide in such a way that if you do up button, then it will show the step by step process. Okay, cool. So what you can do in this particular example, maybe you can write 3 here, you can write maybe 4 here, you can write 5 here, and then you can modify this, right? So see, if you are calling with 3, then this move edi comma 3 will be there. Earlier it was actually 5, and then everything is okay. Then here this int a comma 4. So earlier you were pushing 5, but now you need to push here 4, and then at g you need to push 5, right? I mean, you need to write 5. So the only modification will be this much. Okay, so I hope you understood. The core idea was to just let you walk through of the assembly code. This is completely optional video. It is good that you understood, but otherwise it is completely fine if you have not understood. Okay, so now if you just ask me that what was the purpose of studying all of this assembly code and all, so I will say that this was useful just to let you understand that this compiler generates the addresses based on just one thing, that where you are pushing the activation or where you are loading this particular program in the main memory. So if you recall that there was a problem that we discussed, right? So the problem was that how does the compiler get to know that the physical address we will where we will load this particular program? So answer, we said, like, compiler doesn't even care wherever you are loading, right? So basically, why it doesn't care? Because of this stack pointer. See, like, compiler only cares about the stack pointer. So what happens, that compiler assumes that you have one memory, which is also called a virtual memory or logical memory. So let's suppose I call it logical memory. So you have one memory, and I'm saying that, let's suppose the stack is going downward. Then I'm saying that like, okay, first of all, like, you might not be very much familiar what is this logical memory and all, so don't worry about it. Okay, I mean, you will get to understand in operating systems. So like, there is some stack, there is some heap and all, like, we will see that in the operating system. Don't at all worry about it here. So what I'm saying, like, I mean, you can as I said multiple times, you can completely skip this particular video. So I just explained you that how assembly code are working, because that I was just letting you know that this compiler, based on just one thing, works on just one thing, that where you are pushing your main activation record, right? Or where you are pushing your activation record, I mean the start address. So once you know the start address, right? Once you know the start address, this RSP, once you know the start address, then everything works based on that, right? So every other address is related to this RSP. So which means that you can load it anywhere in the main memory. It doesn't matter, like, you just tell me what is the starting address, and all of these addresses that we have generated, right? All of these addresses are related to RSP. So that's why this is also called as relocatable code. Relocatable code, right? This is also called as relocatable code. Why? Because you can locate it anywhere and it will work very charmly. So there won't be any problem. So what may so happen, like, I mean, you will get to study this later, but I'm just telling you one thing, that you may also divide this particular logical memory, whatever the virtual memory you have, in the further piece of pages or the segments or something like that. And then you can load these pages at the different locations. So basically, there is one more external complexity that get added, and this is the job of operating system, that how to manage these pages, and that's where the paging comes into the picture. So basically, operating system will translate the virtual addresses, that whatever the compiler is generating, these are the virtual addresses only, right? So which is fine with respect to compiler, but the operating system will translate these virtual addresses into the physical addresses based on that, wherever it is loading. Okay, based on that, wherever it is loading. Is it loading to one contiguous chunk of memory? That is called one architecture, which is base bound architecture. Is it loading based on the paging? That is called paging. It is loading based on the demand segmentation or the segmentation, so that is called segmentation. So basically, there are different methods, right? There are different methods to load the program in the main memory, and based on that, the operating system will generate the physical address. So I can say that compiler generates logical addresses, and based on the location, or based on the place wherever we are loading the particular program, operating system translate logical address to physical address, right? So that's all. Okay, I mean based on the strategy that you are using, which means like either using paging, base and bound, and I mean these are the different strategies that we will see later, right? So these are the different strategies that we will see later in operating system. So all of these is actually the operating system part. Okay, so what is the purpose of this video? Again, just to let you know that compiler generates the logical address based on just single thing, that where are you loading this program. Wherever you load, I don't care, let me just generate all the addresses related to that. Okay, so compiler assumes, so I can just summarize in one point, that compiler assumes all memory is available to just one program. It generates addresses based on, or you can say it generates the addresses related to just one thing, right? I mean wherever you are loading the particular program. Okay, loosely speaking, so these things happen, and you will get to understand all of this in the operating system. So this is the, you can say, purpose of this video. So this was the purpose of the video. Cool, thank you so much.